In this lesson, I want to talk about some of the acceleration technologies related to networking. This includes VMQ, SIOV, and receive side scaling. So under normal circumstances, starting at the left side, we have a virtual switch. I have a network adapter at the bottom that has a receive queue and a transmit queue. So a single pair of queues. Data comes into the receive queue. The Hyper-V virtual switch receives the data and works out which virtual machine it should send it to. This takes CPU cycles. It may slow down the processing of the traffic, not by very much, but there is some work that has to be done. With VMQ, the network adapters have more than one set of queues. It has these virtual queues. So the network adapter itself is doing a certain amount of sorting. It could, for example, send all of the traffic for a certain virtual machine to one set of queues. That means the virtual switch no longer has to do that work to work out which virtual machine is this going to. So if I look at a network adapter, I can inquire how many virtual machines it actually has. So I can do get net adapter, VMQ, and I'll just format this output to show me the name, interface description, if it's enabled, and the number of receive queues. And we'll auto size that. So here you can see I've got a number of network adapters. Some of them have got 16. Some of them have 125. So a very large number of queues, probably way more than I'm ever actually going to have virtual machines running on the box. Now these can then get assigned to virtual machines. If I do a get net adapter, VMQ, queue, and we'll just format this as a table, I can see that these virtual machines DC01 and Ubuntu are using a queue. It also maps it to a certain processor core. Then the Hyper-V host itself is using a couple of those VMQs as well, just for the default VM switch. To configure if a virtual machine should use a VMQ, I look at the properties of the virtual machine. I go to the network adapter. I expand that out and do hardware acceleration and say enable virtual machine queue. Now, there's only a finite number of queues. In my case, I have a very large number of them. But the first machines that start, they will take the queues. Others that start later, and if the NIC has run out of queues, would then just run through the regular virtual switch with the shared set of queues. Now, another technology is SROV. And as you can see this time in the network adapter, there are actually these things called virtual functions. These act like mini virtual network adapters. So through SRIOV, which is single root IO virtualization, I can now pass one of those virtual functions and map it directly to a virtual machine. This means that traffic now completely bypasses the virtual switch. So for virtual machines that I enable for SRIOV, they map to a virtual function on the physical network adapter. For virtual machines that I don't enable for SRIOV, then they just go through the regular switch. When I do this, I am completely bypassing the switch, which means any functionality the switch is giving me, like ACL check-in or quality of service or DHCP guard, will not function. But what I am removing is potentially any latency that the switch was introducing. Now, I can still live migrate these virtual machines because behind the scenes, a team is created that consists of the virtual function NIC and a virtual NIC going through the switch. If I live migrate, the network switches to the virtual switch based adapter, it live migrates the VM, and then if available, it switches back to using SRIOV. So it does not break live migration. I can still get that full mobility in my virtual machine. Now to use SRIOV, I have to have the network adapter support SRIOV, and the entire motherboard has to support SRIOV. To use it in a virtual machine, once again in that network adapter, hardware acceleration, I would say enable SRIOV. My server does not support SRIOV, so I cannot enable it on this particular box. I would really reserve using this unless I really find the virtual switch is introducing some latency, some restriction that I can't have. And really the virtual switch is very low latency. This is used for those real top tier workloads that need the absolute fastest networking. But realize that I do lose functionality in the switch when I turn this on. Now the next technology is receive side scaling. Remember I talked about all the traffic has to pass through a single core. Well, that's really a bad thing, because let's say I have a 10 gigabit per second network adapter. A single CPU core might bottleneck that traffic to 3 or 4 gigabits per second. So receive side scaling takes the traffic coming in and it uses, once again, a hash type algorithm to break it up into different blocks of traffic through an indirection table, and then passes that data to different cores on the operating system. This means I'm now using more than one core to process the incoming traffic. Each core would still handle a particular stream of communication because, once again, I can't have that out of sequence processing. I could do get net adapter, RSS, and I could see a state of the various capabilities if I can actually use it. Notice it's only using even cores, 0, 2, 4, 6. It doesn't use hyper-threaded cores. They're not really a true core, so it's skipping those in actually what it would use. It's actually very easy to use this. I just turn on receive side scaling as a property of the operating system. So for example, if I was to open up Device Manager, I could then look at my network adapter, look at the properties of it, go to my advanced, and I'll see receive side scaling. So it's set to enabled. So it gives me now the ability to process higher amounts of traffic. I could also use the enable-net adapter RSS. So enable net adapter RSS would also turn it on. Now you might also notice the RSC, receive side coalescing. When those packets are received, there's often lots and lots of packets, and the operating system has to really join them all back together, combining the payload. With receive side coalescing, some of this work is actually done for you. So it reduces the amount of overhead performed on the actual CPU for the virtual machine itself. Now the challenge with receive side scaling is it breaks as soon as I connect a NIC to a virtual switch. VMQ and RSS are actually mutually exclusive, so I don't get the benefit of receive side scaling in virtual machines for VMs. This changed in Windows Server 2012 R2, which introduced virtual receive side scaling. Here, I still use the virtual machine queues, but now the Hyper-V host does some of that splitting of the traffic for me. It sends it to the multiple cores inside the virtual machine. So the VM must have multiple virtual CPUs, and now the Hyper-V host will send that through and split up the traffic. I enable it within the VM exactly the same way. There is one additional new technology. Windows Server 2016 introduced something called Virtual Machine Multi-Queue, or VMMQ. The reason for this is, as you saw, modern network adapters have a massive number of cores. More cores than I actually have virtual machines running. If I go back and look at this, remember 125 queues. And so rather than having to have the Hyper-V switch going and working out splitting up traffic over multiple cores, with VMMQ, I assign multiple hardware queues from the NIC and then allocate them to a single virtual machine. Each queue is affinitized to a specific CPU inside that virtual machine. Now, the multiple queues are handled within the NIC hardware using the same hash type algorithm used by RSS. So now, instead of the VM switch having to do that hashing and CPU overhead on the VM, it's actually now happening directly on the NIC adapter and saving me performance on my Hyper-V host. To enable VMMQ, I simply do set VM network adapter, the VM name, and then VMMQ enabled to true. That will then use the new technology and assign multiple queues to the VM and to save some overhead on the Hyper-V host.